So we're going to talk about the implementation of precomputed atmospheric scattering that we implemented in Radiance for the purpose of generating spectral sky. So why are we doing this? So I think it's pretty obvious. So why we want to do hyperspectral simulation. One of the reasons is as for better accuracy overall, not just for both visual and non-visual application. And then in order to do that, we need input data. So for the material, we have opaque surface, we have the spectral material database that Austin managed, and we have LBL's international glazing database that we have. Those are all spectral data. We don't have a spectral BSDF data set. That's still to do. For the light source, we have some kind of artificial light spectral data, but we don't have daylight yet. So that's the purpose of this work. So why is the sky the way they are? Why is it blue? Why does it look like that? For the intended purpose of modeling, we simplify the scattering behavior of the atmosphere to two parts. One is Rayleigh scattering. One is Mie scattering. So Rayleigh scattering is basically when an electromagnetic wave hits any particle that are smaller than the wavelengths. In that case, it's mostly the air molecules that are in the air. So that's what gives the sky blue color. Mie scattering, in the other end, is mostly caused by human or volcanoes that are dust or soots or water-soluble, insoluble particles that are floating in the air that we colloquially call aerosol. Those particles has wavelengths that are larger than the electromagnetic waves, and then the scattering behavior of those particles are usually much more complex and then asymmetrical. That's what gives us the directional scattering of the sun, essentially. So this diagram shows you that, for example, when the sun, when you're looking at the low angle sun and then you're facing it straight, you're seeing both. You're seeing a really strong Mie scattering that is aerosol that's give us the really strong scattering around the solar area. And then when the light is coming from overhead, you get much less Mie scattering. You get more dominant Rayleigh scattering. That is why you can see the rest of the sky is pretty blue. As a result, on the right-hand side, you can see how we break down. So if we don't simulate the Mie scattering, just the Rayleigh scattering, that is very homogeneous sky, just a very blue sky. When we take into account the Mie scattering is just usually is pretty flat across the spectrum. So it's usually a gray neutral color. And then when we add them together, that's what we expected a sky to behave. So let's first talk about the Rayleigh scattering. So on the left is the altitude. It's a profile of all the air molecules as a function of altitude. Their concentration on the Y scale you see is in log scale. So essentially, all the colored ones at the bottom, the lines at the bottom are individual air, like oxygen, ozone, and then other particles. And then the blue one at the top is considering all of them together. As you can see, the blue line is pretty flat. Usually that is the case because those particles are pretty well behaved. So we can pretty much assume a exponential decay of those air molecules as assumption for our modeling. So we can, on the right-hand side, you can see this equation that we can assume a certain scale height as a you can think of it as a factor or ratio, and then this exponential function defines how does the concentration of the air molecules decays over altitude. So that gives us a pretty convenient way to simplify this. So we can basically tune the scale height. On the left, you can see that various scale heights give us a different decaying profile. We just have to tune them to match some measurement data that we have. So for the purpose of developing this model, we just grab the most used measurements that is pretty old. So it's probably not that accurate. So if anybody has any more accurate data, like consistent global data that we can use, it's great. Because for example, as if we go back, the purple line here is CO2, for example. So the CO2 concentration level rised from around 300 parts per million to about 400 now. So the measurement data we see here was measured in the 80s. So the CO2 concentration between 80s and here is about 50% increase. So as a result, I don't remember the exact detail how CO2 impacts. CO2 impacts the humidity, the water concentration of different particles, so that will impact the scattering. So, but anyway, this is the best we can do. So this is measured by the U.S. Air Force Geology Lab, I think, across the globe. So we have essentially 5 profiles. We have mid-latitude and then subarctic and tropical in terms of latitude range. And then we have summer and winter for the mid-latitude and then the subarctic region. So essentially we tune the scale height across the spectrum. So the horizontal column here are essentially 450 nanometers and then 560 nanometers and then 670 nanometers. But we're only showing these 3, but we basically show the whole, did that for the entire spectrum range and then tuned it so that the differences between our simplified exponential decay is matching the measurements as closely as possible. So that's Rayleigh scattering. And then for Mie scattering, we cannot assume exponential decay anymore because it's quite complicated. As you can see on the left here is another measurement data set. The data points are pretty sparse, but they're pretty irregular. So this is insoluble water, water soluble, and soot, and then I don't remember the last one, but and so as a result, we feed this data sets, measurement data sets into a radiative equation solver, and that gave us the scattering coefficients of or the Mie scattering across the altitude. So each line on the right hand side is for a spectrum, and then this is how the scattering coefficients behave across this height. So it kind of so again is log scale, and then it just dips really fast and dips much slower and dips really fast again and stays flat and it increases again. So it's pretty irregular. So we can not simplify that with a exponential decay. So we kind of have to use that data directly. So this is one of the modifications that we did for this implementation is that we were able to use any type of Mie scattering data directly into the simulation. So the overall data flow is the only light source in this simulation is extraterrestrial solar. So the solar that's arriving at the outside of the atmosphere, that's our only input source, and then input light source, and then the radiation will interact with the air molecule, aerosol, and ozone. Ozone is one that I didn't talk about, but it was just simply absorption profile. So all ozone does is absorb. So these 3 phenomenon we interact with, and on the right is our output data. So it's for any point in the sky, we can query and look up the spectral distribution. So this is schematically a simplified version of what we do. So we have a sphere that is to scale of Earth. So it's 6,360 kilometers, maybe. And then we model our atmosphere in 60 kilometers thickness. So we would send rays from the point on Earth towards all possible directions, towards the outside of the atmosphere. And then we would do numerical integration along the rays line, and then send those rays to the sun. So this is called a single scattering. So this is only if we're considering the lights directly coming from the sun. So we would do this for a bunch of directions, and then we would get a single scattering from the sun. But single scattering is really not enough, so we have to do multiple scattering, and then so this is when we have to consider the in-scattering of a lot of positions across the atmosphere layer. And then that would consider, so for every single one of these incident direction, we would do another numerical integration that sends a bunch of rays to the sun again, and then integrate along those paths. As you can see, that those computations can become very intensive. So the overall algorithms that we implemented is developed based on the Brunetten and Nayrad algorithms that published in 2008. So as a result, there are 4 pre-computed tables that we can use to sample our sky. One is transmittance, and the other one is irradiance, and then single scattering mean, and then also multi-scattering mean. So I'm not going to the details of the exact algorithm. You can go to the paper. So we follow the exact implementation of the derivation of these 4 data sets. So essentially, we have to sample 2 or 4-dimensional grid over the sky dome. As I mentioned earlier, we use those standard Rayleigh scattering profiles, and then automatically pick those based on the input latitude, longitude, and daytime. And then we use the standard OPAC continental average aerosol profile, but we can provide a custom one. And also you can do linearly scale those aerosol profile if you have that data. So this is what the pre-computed texture looks like. So essentially on the left is 2D, on the right is a 4D that's projected into 3D. So on the transmittance, it's pretty straightforward. We pre-compute for a lot of cosine view angles and a lot of altitude, and compute the transmittance to the outside of to the top of the atmosphere layer. And then same as for irradiance, on the right is scattering coefficients that we compute at a bunch of cosine view angles and then a lot of altitude angles. And then we compute them for also a range of solar angles. So that's 4-dimensional. And then they all have one actual dimension, which is the spectrum. So we do that for our entire visible spectrum. So as a result, we have a program, GenS-Sky, that generates the a hyperspectral image that is our sky map, hyperspectral sky map. So one of the shortcuts we did is that the model itself only do clear sky. So we don't have a way to do clouds. So the way we do clouds in this program is to linearly interpolate between a clear sky and an overcast sky. So as you can see, if you have a cloud sky cover of 1, that will give you a CIE overcast sky. You have a 0, that will give you a pure clear sky. And there's a -D option to linearly scale your aerosol profile up and down. And then for the output hyperspectral image file names, there's a default one, but you might want to change those for if you want to do a lot of different runs. And then for the P is for saving the pre-computed data, so you can use it later. So essentially, if you run GenSky in the same latitude range and same seasonal range, you will go look for that, go look in that directory and trying to find the correct data files. And then if you already pre-computed before, it's gonna just grab those and use them directly. So if you can't find it, it's gonna do the whole pre-computation again. And then for the ground, we have a neutral ground. We probably want to change those to be spectral at some point. So right now it's only a neutral ground. And then also the hyperspectral sky map has a resolution that is the equal rectangular projection with X resolution and Y resolution is X divided by 2. So this is one of the important piece of running GenSky is that if you have a custom me-scattering aerosol profile file that you want to use instead of the default one that comes with it. So it defaults to using this one that CA stands for continental average in the ray path that will get installed. But if you want to use a custom one, you can generate those. So this is the format of the spectral. So this is the spec.dat primitive data files that Greg talked about in the morning. So it's a two-dimensional data files, spectral data files. The first dimension is the altitude dimension. So here I have an irregular altitude data points going from 0 to 60,000 meter. And then the second dimension is spectrum. So it goes from top to bottom. So going from the spectral range to the altitude. So that's your entire me-scattering coefficients. The units are in meter. So each of the scattering coefficients is in per meter. We also have a GenS state matrix. So GenS state matrix is essentially using the exact same model. So instead of generating a sky map, we're just generating a Triganza sky patch. So the same parameters we have for the Gen day matrix that you're familiar with. The only difference is that we added the -p for the pre-computed directory path, and also -n for preprocessors. So actually this is threads, not processors. So this will both GenSky and then I don't have it here, but both GenSky and the GenSday matrix is multi-threaded that should work on both Windows and Linux natively. And then because GenSday matrix use the aerosol and then the total sky cover. So we modified the EPW to WA to output those values from the EPW files. So this is essentially the workflow. You run it with the -a options on your EPW files, and you can pop that directly to GenSday matrix. So here we have Reinhardt 4 division with daylight only hours. And then that will output your spectral sky, annual spectral sky matrix. So this is some of the sample renderings with the sky cover. So this is the variation in solar altitude. So we have a 50-degree, 10-degree, and -4 degrees in terms of solar angles. The solar radiance, the sky radiance all change depending on the solar angles. You can see that based on the color of the sun patch on the desk here. So this is another set of examples showing the variations in cloud cover. So going from 0, so clear, to 0.4 and 2.8. This is a variation in the broadband aerosol optical depth scaling. So the the middle one is close to the default. And then the left one, we set it to a much lower clear sky value. So basically half the original default value. And then the right-hand one is basically double the default value. So that means this ideally, without changing the overall scattering profile, we make the air looks dirtier or cleaner.
Does that have an upper limit?
No. You can be, yeah, I haven't tried it, but you can probably make it all black, like inside of fire or something. So the next step is in a particular order is to have a better cloud modeling. And then that's probably in a, so actually model the geometry, the shape of the cloud instead of a homogeneous layer across the sky dome. And then also we want to be able to validate this entire model against measurements. Help welcome on that front. And then we want to also be able to normalize the entire sky based on a broadband measurement, such as direct normal and then global horizontal irradiance, sort of to calibrate the overall simulation results. And also we want to be able to add options to either increase or decrease the number of channels. The last thing is that there is also another tool that I developed because I had to sort of check against kind of a standard industry standard workflow that's using Libra-Trend. So Libra-Trend, for those who don't know, is like sort of industry standards, highly accurate radiative transfer solver. And then so I sort of compare our model against those. And in the process of doing that, I kind of developed this wrapper around the Libra-Trend process that similar workflow but you have to have install your Libra-Trend first. So this is only calling that. And then it also generates the exact same thing that GenS Sky gives you, which is a hyperspectral image. And then you can just use those and then you can do comparisons side by side. That's it.
So it seems to me like the first part you were explaining basically development of functionality model, right? Have you compared that to some of the existing ones like the Angstrom or the Lake or the Bergen-Folstrom broadband neural optical depth?
No.